When flipping a coin 4 times, there are 16 possible outcomes. One of those outcomes has no heads. There are 4 outcomes that have 1 head, 6 outcomes with 2, 4 outcomes with 3, 1 outcome with 4. We could list 0 and then 4 1s and then 6 2s and then 4 3s and 1 4 in a column. We could add those numbers up and we could divide by 16 to get their mean. Or we can just say, well, if we're going to have 4 1s, that's going to total 4. 2 6s will total 12. 3 4s will total 12. 4 1s will total 1. We add those numbers up, and again, we get 32. And then when we divide by the 16 outcomes, we still get a mean of 2. And we can calculate the standard deviation also. It turns out that's 1.03. Now, the problem gave you the results of a simulation where we used a random number generator to determine whether a given flip would be a head or a tail, and we did that in groups of 4 flips, and we did 64 trials. Okay, these numbers only add up to 63. I miscounted something. So when doing that, we found that, or if you did that, if you tallied the results on the test, you found that 0 heads occurred once, 1 head occurred 14, 2 heads occurred 27 times, 3 heads occurred 19 times, 4 heads occurred twice. So we wanted to calculate the mean. Well, no heads occurred this one time. That's not going to contribute anything to the total number of heads. 1 head occurred 14 times. That's going to total. That's going to contribute 14. 2 heads occurred 27 times. That's a total of 54 heads, and so forth. And we add up these numbers, and we find that we got 133 heads on 63 flips, so that the mean was 133 divided by 63, or 2.11. Now everybody should understand this quite well. And then if you remember the definition of the standard deviation, it should be pretty easy to go ahead and calculate the standard deviation. Now, the definition of the standard deviation, as we used it in class, is that it's the square root of the so-called mean of the squared deviations. The quotes around the mean, so-called mean, because if there are fewer than 30 outcomes, now in this case there were 63, but had there been fewer than 30, when we calculated the mean, we would have had to divide by 1 less. And we talked about the reasons for that, but that's the rule. Okay, so what we need to do is calculate the deviation of each of these numbers from the mean, which is 2.11. Well, 0 differs from the mean by 2.11, 1 differs by 1.11, and so forth. 4 differs by 1.89. Now, we got the deviations. Squared deviations means that we square the deviations. Okay, then the mean of the squared deviations, well, we add up all the squared deviations. Now, we don't add up just these numbers, because this is what we get if we just had 1 0, 1 1, 1 2, 1 3, and 1 4 in our outcomes. We have 14 of these, so we got to add 14 of these, and we just multiply, of course, 14 times this to get what we would get if we did add 14 of these. 19 of these gives us this, and so forth. So these are the total deviation squared corresponding to each value of x, according to the number of times that value is observed. We add these numbers up, we get 44. That's a total of our squared deviations. Now we want the mean of our squared deviations. We don't need to worry about the quote around the mean. Since we have over 30, we divide by the full number of outcomes. So 44 divided by 63 gives us our mean squared deviation. And then the standard deviation, remember we had squared deviations here. It makes a certain amount of sense to take a square root. So the square root of the mean of the squared deviation, 0.84. And this is a measure of how much that distribution spreads. Now, you weren't asked to do it, but I went ahead and constructed normal curves. One with a mean of 2 and a standard deviation of 1.03 corresponding to the ideal. Another with a mean of 2.11 and a standard deviation of 0.84 corresponding to the simulated distribution that we obtained just using a randomizer. Okay. Now these curves should have equal areas underneath them, and it's plausible that they do. Standard deviation here is a little less than here, so this curve is a little narrower than this one. So as a result, it has to be a little higher in order to have the same total area, and it pretty much has those characteristics. I wouldn't want to hazard a guess as to which one actually has the greater area, but they're intended to be identical. So, and we also just, these would correspond to our z values, -2 for 2 standard deviations below, -1, 1 standard deviation below the mean. If you don't understand all that, look at the longer explanation. And I'll also comment that these two curves show that we've got pretty good agreement between the ideal and the simulation based on 64 coin flips, but we just used 63. I don't know which one I miscounted. Had we actually flipped the coins, we could have, with equaling likelihood, obtained this outcome, but we would very likely have obtained another one. Based on a 63 trial mean and standard deviation, again, the two curves, the means and the standard deviations, are in pretty good but not perfect agreement. Had we done many more, and of course it'd be easy to write a program to simulate many more flips, a little harder to actually do all the flips. If we did, say, 1,000 flips, we would expect the means to be even closer than they are here. Okay, and we would expect the standard deviations to be closer. If we do more and more flips, greater and greater numbers of flips, we expect these two curves to approach the same. We expect this model here, this curve, to approach this one.